The purpose of this lab is to observe, quantify, and predict the motion of a falling object by utilizing Newton's second law. In order to successfully analyze this experiment, one must take into account both the effect of gravity and the effect of drag. The first step of this process was utilizing tracker. An eraser having a mass of approximately 0.045 kilograms was dropped from a height of 2 meters. An iPhone was used to film this experiment, which recorded at approximately 30 frames per second. The video was calibrated using the tape measure placed next to the eraser, which is set at a height of 2 meters. The origin was placed at the center of the eraser, and the coordinate axis was defined to be -y for the downward direction. In each frame, the center of mass was marked to track the downward motion of the object. As the video progressed, however, the eraser became blurred, so in order to maintain consistency, the bottom of the blur was marked. This was done so that when the eraser hit the ground, the final frame could be identified, and thus the total time taken for the eraser to fall could be defined. The total time for the fall was approximately 0.6 seconds. After the experiment was conducted, 2 computer models were created using PHYS in order to predict the motion of the falling eraser. The first model made the assumption that the only force acting upon the eraser was the force of gravity. The initial conditions were defined to be the same as the real-world conditions themselves. The change in time was defined to be 0.033 seconds. As expected, this model overestimated the final position of the eraser. The second model, on the other hand, needed minor changes in the code in order to account for the force of drag. There is no easy way to find the drag force, so finding the values that fit the model the best was a trial and error process. The drag force was then added into the while loop in the VPython code and was defined to be equal to some arbitrary constant b, defined to be 0.023, multiplied by the magnitude of the velocity squared, and then finally multiplied by the directional vector j hat. The net force of the falling eraser was now defined as the drag force plus the weight force. This model proved to be a more accurate representation of the real-world results. The experimental setup made it somewhat difficult to state whether the eraser reached terminal velocity during its fall in the video, and numerical data showed that the eraser was falling with increasing velocity, but there are signs of the object reaching terminal velocity at the 0.045 second mark, which is when the position versus time graph starts to develop a constant slope, which indicates constant velocity. If the eraser had been thrown down instead of dropped down, the terminal velocity would have been the same. While the eraser's downward velocity would have been increasing, there would have been a non-zero net force, which would have meant that the drag force would have been smaller than the gravitational force. As time progressed, however, the net force would have been zero because the velocity would no longer be increasing, which means that the force of air resistance would have grown to be as large as the gravitational force.